Okay, that looks like it. Yep, thanks for the introduction, Dan. Um, yeah, so where do I start with this? As Dan was saying, this is work I was doing before I started at Huawei with Bob Atke, who seems to be here. So hello, Bob. um, and this is well, rather embarrassingly, I haven't updated one bit of the title slide. So this is based on a talk I gave half a year ago, before I'd actually done the research. Then I did the research and then realized, oh, I talked about it recently, but before I did it, so I built up for that. Yeah, so where are we starting with this work? So back in 2005, Conor McBride, well, not really published, but wrote a note about a nice way to prove renaming substitution for a simple type system when you're using de Bruijn indices. And this idea was kind of incubating for a while, and in one of these years, there are a bunch of Strathclydes and others who worked out how to not just do renaming substitution, but also semantics, so mostly denotational semantics. But they could do other sort of general traversals of terms in a nice way that dealt with variable binding rather than doing it all manually. And then sort of in parallel, Bob and I had been working out how to adapt these renaming and substitution proofs from simple types to linear or quantitative type system. And this talk is, well, eventually this talk is about bringing them all together. I'll start with a complete introduction of everything here. And shall I say this now? Yeah, so the idea of the left is that the linearity or usage awareness should be independent of the binding structure. So variables kind of exist as if they were an intuitionistic system, but then we annotate them to say how they're used. And this other side is all about generic programming of things that look a lot like type systems. Yeah, and the way the right-hand side is achieved is eventually we get to a point where everything is stable under renaming or stable under structurality, as I've called it here, which we'll come back to later. But the idea is to kind of give yourself a bit of leeway in terms of structural rules, and that's kind of what natural deduction is supposed to do in a way. So you give yourself that layer to work on, and then get going from there. And what they do, they have a single generic traversal over syntax that you can repurpose to do different semantics, listed here. And furthermore, they and we eventually consolidate all the possible syntaxes into a kind of this, you build them up like Lego kind of thing. Each typing rule is made of little bits and fit them all together. So start with Connor's stuff from 2005. What was he wanting to do? He's wanting to prove substitution, which is the thing on the right. It says if for every variable in some context I can produce a similar term in a new context, then I can map the terms similarly. There's some awkward notation here that why is it a backwards turnstile, but you can read that as forwards turnstile but backwards. And you think, okay, so the idea is to traverse through the term. When you reach a variable, put the term there, otherwise do structurally, except when you bind new variables, you have a bit of difficulty because, so I've conveniently got the types of things over here. You want to turn a lambda, which binds a variable, into a new lambda that binds the same variable, this x. So this x has been bound in M, and somehow we want a substitution that works not from gamma to delta, but rather x gamma to x delta. And we have to do a bit of work. So there's this bind lemma that looks at, basically says, are we looking at the x, the new variable, or are we looking at some old variable in gamma? The new variable, it's easy enough. We pick out this x here, turn it into a term. But in the other case, so from sigma I, we get, because I is in gamma, sigma I, we can apply to get A in delta, but to turn it into a term of type A in context X delta, we need renaming, and renaming has basically the same structure as substitution, so we end up duplicating a lot of code. So instead, we generalize over the red things, basically. So the difference between renaming and substitution is what you replace the variables with, and we just say replace them with an arbitrary thing that satisfies a few properties. And they're quite easy properties. So you can turn, we call these V things values. You can turn a value into a term, and use that when you hit a variable, use the environment sigma to turn it into a value, and term to turn it into a term. And to the other things. So you can turn variables into values. That's when you have a newly bound one. And this property down here that if you have a context delta that's an extension of gamma, then you can kind of lift variables and lift values, sorry, from gamma to delta, where this here means renaming. Okay, this is a convenient point to stop for questions if anyone's lost or whatever. Okay, I'll carry on then. So yeah, this is kind of my 2-slide introduction to Connor's 5-page note. And so this is nice. You can prove renaming substitution and one or two other things, possibly. But when we talk about semantics of a term, we really want to map it not into some, we're not just mapping terms into terms, we're mapping them into something else. And for that, we already made this V kind of arbitrary, and we've got a C for computation. And so similar kind of form, we have an environment that maps variables to values. And we get out at the end, excuse me, that we can map terms to computations. As long as we have this structurality condition, the str from last time. And now it's not quite so easy to say go structurally, because we don't know that C has term formers. We don't know that it has application of lambda or whatever. So for now, we're going to add these in kind of manually. So yeah, what do I want to do? Yeah, I'm going to introduce some new notation. So instead of this environment being a function, you write it like this. Same thing. There's also the question of why do we call it semantics? Well, you can think of if you want a denotational semantics, what you can do is set C to be some set of semantic morphisms based on, morphisms from the interpretation of gamma, the interpretation of delta to the interpretation of A. And then you set delta to be gamma, so that and V to be variables, so this can be the identity, and then you get a mapping from terms of type A in context delta to semantic morphisms from gamma, from gamma to A. I should have had a slide for that, but ran out of time. Right, and what's going on down here? So there's all these funny boxes which are needed basically because the new variables are not just the variables we have now, but the variables we have later as well. So this is the idea that T doesn't just hold of gamma, but it holds of any extension of any renaming or unrenaming of gamma. So what do we get? We can turn values into computations. This is taking the place of term from last time. And applications. This should look like the typing rule. So we have a computation of type A to B, and a computation of type A, giving a computation of type B. Oh yeah, maybe I should explain the for all. This is this basically says for all gamma, this entire expression at gamma, and these dots mean pointwise across contexts. And then the interesting one is lambda, where we bind a value of type A to get a computation of type B. From that, we'd want a computation of type A to B. And okay, these are all these are mechanically derived from the typing rules. So we're going to formalize what a syntax looks like, and it can a syntax or a type system can have multiple rules. Each rule can have some premises connected by times, dot times, and the premises combine variables. Variable rule is a special rule that we don't describe It's just there. And yeah, these are some examples of descriptions. So the application rule at A to B, or A and B, has one premise, which is the function, one premise, which is the argument, and a conclusion, the result. Meanwhile, lambda is binding a variable A. This is what turnstile means in this case. The forward turnstile means binding, whereas the backwards turnstile means term. So we bind A to get a B, then we can conclude something of type A to B. Right, and okay, last slide before another break for questions. This is how you compute the semantic requirements for the semantics off of the descriptions. So you introduce this kind of scary looking thing called Kripke, which is basically of the form, maybe I should just go back to the slide. It's supposed to be kind of one of these things. So you can see the box and the collection of premises, etc. And these variable bindings, we could bind multiple variables, so we end up with an environment worth of them. So once we add these variables in gamma as values in the current context, we should be able to produce computation. Okay, yeah, and assume D is one of these descriptions from the previous slide. Then we can take what it means to be one layer of this and plug in these requirements, the old semantics of var that turns values into computations, and the semantics of a generic constructor of syntax, where we've got kind of one layer of syntax on top of basically on top of this semantic stuff like computations, and we need to be able to turn that layer into semantics. And traversal is going to look similar to before. We have a similar bind lemma, and variables we use environment and var. Then for all the other terms, we use the generic constructor interpretation, and this one layer is suitably functorial. So there's a map that lets us get at the smaller terms, and traverse them. Okay, that's another point where I can stop for questions. So this basically summarizes the AACMM stuff. So we've got intuitionistic syntax and semantics. Next slide. Some scary looking typing derivation, but so the point why I include this is to emphasize what invariance the AACMM stuff was. Maybe I should say LA et al. It's kind of easier. What invariance that was relying on. So I think these come out quite nicely. So you start with a closed, trying to produce this closed term. Conspicuous use of linear logic notation, but anyway. So you start making this closed term, and you can bind things. So lambda p binds the p. Pattern matching eliminator of the pair binds the f and the x. And we still keep p around. P is just on its own on this side, still around. And then the only time we really talk about the context is in the variable rule. So we pick out this p immediately. We pick out the f, and we pick out the x. Right, so we haven't done anything to the context other than add to it in various places, which is exactly what all this crypt code stuff was taking account of. Right, and then when we care about usage in, for example, this is supposed to be a something like a linear type system. What we're going to do is use this quantitative type theory style, or it's related to the granule stuff that what Petrocek Orchard Eads have been working on for a wee while. So we say lambda p means we get in the body one use of p. And what we've done here is, because we only get one use, we send off this one use to the left where we need the p, and leave it with 0 here on the other side. And similarly, the pattern matching, you bind one use of f and one use of x, and we duly use them on one side or the other. So the difficulty here is we kind of breaking the assumptions of Allais et al. By having this bit of the context that that gets modified everywhere. So things are changing from ones to zeros, and also we can't just expect to bind new variables arbitrarily, because we don't have weakening. It's not in general. So we've got to work out something to do. Yeah, I guess I'd take questions about the idea of usage annotations or quantitative stuff at this point. So I'm going to make the point over the next few slides that these changes are not completely arbitrary. So there are in fact only a few things we could want to do. So reading from bottom up, here are two of them. So this one we saw on the last slide. The idea is that we can require that the usage annotations of the conclusion are split up into smaller ones. So you think of these as like a 1 on one side, a 0 on the other, or a whole vector worth of that. And then we can add them up along their lengths. Oh yeah, notation. Little gamma is the types, whereas PQ and R are the usage annotations. They should be a kind of brighter green, but they don't seem very visible on my screen. Sorry if they don't look so visible where you are. Other thing we can do, so this is a kind of prototypical rule that that requires this addition. We're creating a tensor product, and we kind of split up the what we're allowed to use for the left part and the right part. That's what's going on there. And its unit, the tensor unit, we require that all the variables are to be used 0 times, because there's no space to use anything. And 2 more things. These are the last 2 things. So maybe I should do it the other way up, but I don't know. Yeah, I'll do it the other way up. So this is something that comes up if you want to interpret the bang, the exponentials of linear logic that let you use things multiple times. So if we're just talking natural numbers, this R is like saying we have an A value that we can use R many times, 2 or 3 times or whatever. And in that case, we require everything in this conclusion to kind of support that by there being many copies of everything compared to how we've produced M. And this one's a bit funny, the variable rule. The variable rule needs that X can be used once, and everything else is used 0 times. And if we kind of remember back to I don't know, first year linear algebra or whatever, we spot that this is the basis vector at X, the variable we want. So the X notation 1. So these are all them together. And it's quite nice that these are the kind of most standard linear algebra operations, at least that I know, on vectors. And we can see that these 3, that the 0, the plus, and the scaling are exactly the things that when you have a linear transformation, they distribute over it or whatever, commute with it. I guess the basis vector is a bit special, so this only comes up in the variable rule, and as we said, we don't describe the variable rule in our descriptions, so we don't need that to be preserved in any way. But when that meets a linear transformation, the basis vector is going to map to something fairly something characterizing the linear transformation. So that's a good sign. Also, in all these rules, we can see that although we can't have weakening in general, we can weaken by 0 use things. So I guess if we got a vector full of zeros, that's the requirement, and we add 1 more 0, it's still 0. If we add a 0 then to these 2 halves, the P and the Q, we could add their own 0 on, and that's going to sum to 0. Multiplication similar, or scaling I should say similar. And for variables, as if by magic, a basis vector to which you add an extra 0 is still a basis vector of the basis of a one-dimensionally higher space. So that's great. Oh yeah, one more piece of notation. I use this variable thing is really important. So I abbreviate variable of correct type and usage annotations basis vector by Mike Schulman's square in, which I quite like. Everything becomes a bit more square following the Schulman principles at this point. Right. And this is kind of giving symbols to what we saw on the last slide. So when we talk about descriptions, we're going to use things like this star to say we separate out. So let's read what it says. We start with an R, we separate it out into P and Q and require things in the P's and the Q's. Got a unit which asserts 0. And the scaling one that, we split R into P R many times. And require things. And then we get description looks like this. So we separate one premise is a term of type bang RA. The other premise binds at annotation R, variable type A to produce a B. That's the continuation of this kind of pattern matching bang elimination. And then we conclude a B at the end. So we generate syntactic rule, semantic requirement. And somewhat funny has turned up in this semantic requirement that because we're talking about adding in newly bound variables, we use this separating conjunction, the magic wand, to say we want the conclusion to be in something bigger. So we take in Q kind of extra from the new variables to be able to make the conclusion. And worth noting at this point, it might seem a bit strange, but it's true that we really do have like a bunched implications style thing going on here. You might sort of imagine that this is just linear, but we really have a distinction between these two arrows. Both of them is monoidal closed. This one's still Cartesian closed because we still have the dot times to go with it. Whereas this one, the wand, is monoidally closed with the separating conjunction. I think that's quite neat. Yeah, this was noticed in this paper down here. I think there's a longer version of this now that was at Popple. So Popple 2021. Of that. So what do we need to update from the old stuff? Well, so we talked about this separating conjunction. So this is adding in all the extra values from the newly bound variables. And so we've dealt with that, but we have to deal with what's an environment now. So one of the things we want is that this expression here with the separating implication, the magic wand, basically should curry out, using. So if we bind multiple variables, that should be the same as binding one wand, binding another wand, etc. Which leads us to this thing here, that if we bind two contexts, gamma and delta, that should be equivalent to separating apart this source context along the middle, and then splitting out the target context, not along its length, but rather kind of added together. So you get two two target contexts, still of the same length, but the usage annotations have been split up such that they add together to produce the original one. So that is occurring. The obvious unit law, if we bind nothing, that's the same as something that just gets rid of, makes the wand kind of useless. And if we come across a variable with a particular annotation and we want an environment for that, that should be the same as scaling a value. We kind of saw that as well when you, I guess that I implicitly used here, is having arm any of the value of the certain type. Right, and you could take this as a definition, but it's really crap to work with. So, for example, it's difficult to prove the identity renaming, because first, so you start with, you want some kind of gamma comma delta to gamma comma delta. The first thing you end up doing is gamma to gamma comma delta and delta to gamma comma delta. But them two subparts are not no longer identity of the identity form. So you got to do some annoying stuff to deal with it. So instead, we come across this definition where, so we sort of take the idea of this builds up like a weighted sum of copies of the target with different annotations, weighted by the annotations, summed by this rule. And the linear algebra way to do weighted sums is to do matrix multiplication. What's this saying? So this is an environment of square variables, as I like to call them. And we want to split up this target usage vector, the 6010, into one part is 0010, which we multiply by 1, 1000, which we multiply by 2, another 1000, which we multiply by 4 in this case. Those coming from over here. So when we do this multiplication, we get back this as desired, and in each row, if you see each row as its own, it's like a small version of Q. It's its own usage vector, and you pair it up with the old typing context that just gets copied everywhere, and you see, oh yeah, if I had that, 0 A's, 0 B's, 1 C, 0 D's, I could get a C variable. If I had 1 A, 0 of everything else, I could get an A variable, and I could get another A variable. So this is how I kind of draw it out. It's written formally down here, which I'll talk about later. So this is a dual purpose example. Instead of the subset, I'm going to do a squarer one to show that this is a renaming, and renaming is super important. And if you look at the example rather than the sort of matrixy stuff, you'll notice that what's really going on is I've done an exchange to push the C in front of the A's. I've done contraction to turn 6 A's into smaller. 2 add 4 is 6. That's the important property here. And weakening to weaken away these zero-use things. So this is usage annotations controlling what structural rules we can use in our renamings. That's how I like to see it. This contrasts a little bit with substitution, where in substitution you're not just doing structural rules, you can actually use term formers and derive things. So less trivial. So here's one you can do at home. So what do we require of an environment from gamma to delta, or p gamma to q delta in general? P gamma q delta. We have to pick this matrix, this linear relationship, such that satisfies this on me. So usage annotations change throughout the derivation, and what we really care about is not p, what we started with, but rather p when we get to a variable. And p when we get to a variable, this p prime is it's really going to be a basis vector, because it's a square variable. That's what they do. So whenever we get to a basis vector, then we should be able to produce a value in a similarly related. So this is no longer a basis vector. It's the image of a basis vector under a linear map, which is arbitrary. Same types. What's after that? Yeah, so we get back to the semantics, and it turns out nothing really changed. So as long as we tinker with the innards, everything becomes back to normal. We just need semantics. The values are stable under structurality, where we have this kind of nuanced notion of structurality that cares about usage. We have these brand new environments, but they're kind of similar in spirit. And then Kripke, we also modified. It's all the same form. And then when we come to prove this thing, we just got like loads more algebra to do, but it's basically the same idea. Right. Okay, any questions? I think all I've got left now is a few more examples. I'll probably just do the examples, to be honest. Okay. Yeah, so so you can find examples of semantics in the Alay et al. Paper. Has some nice ones. Not well, very few of them I've re-implemented for this usage aware setting. But a new one I've come up with is the generic usage checker. So without knowing anything about the syntax of the type theory you're talking about, you can write something that takes an unusage aware term and turns it into a usage aware one, or at least tries to. So what's the idea? With simplicity, just let values be variables, and the outputs of the traversal are going to be, they take a desired usage vector, or decide usage annotation for each free variable, and you kind of non-deterministically give back well usage derivations over that kind of look like the original term. And so you require the semi-ring to be able to spot what's 0, spot what's 1, and with stuff like addition, we're going to do, this is where the non-determinism comes in, that if we had a 3, we say what adds up to make 3, and we get all these different pairs of things that add up to make 3. Scaling similarly. So this is, you're working from the bottom, you try to share out, and you basically try all these, see what works. And then we take cases on the description elements, these, how many are there? 5 things. Rather than on the entire syntax, we just deal with the building blocks, and there's very little, if any, duplication of code. That's quite nice. And yeah, we traverse the unannotated term, and we'd usually start with a closed term, so we don't even have to provide an R. That'll become, as new variables get bound, that'll get some real values in it. And yeah, this is a massive quality of life improvement if you happen to be working on simple but usage-aware type systems. Can recommend. And also testing the kind of testing the ability of these descriptions. You can do classical linear logic, not just intuitionistic things. So you take a kind of natural deduction presentation of classical linear logic. This one, I'm not going to bother pronouncing the French words. Okay, so you're doing some serious proof theory when the important article's in French. But so what you do is, instead of, previously we just talked about conclusions of judgments being types. So you have a variable type A, and that's just a thing. But we now instead split between, in mu tilde terms, a term, which is kind of like a proof of A, coterm, which is like a refutation of A, or a command, which is like a what do you call it, like a contradiction. And you can have variables of these things. So hypothetical term is a variable in the mu tilde sense, and co-terms, co-variables, and the variable rule, the standard variable rule kind of just works. And got a couple of example descriptions. So if you take a term separate from a coterm, you can derive a command. So this is proof and refutation gives a contradiction, as long as you can have them in the same setting. And if you want to produce a term in the mu tilde world, you can instead bind a coterm and look for a contradiction. Okay. So that's about it. So what have we done? We've taken the Allais et al. Framework and worked out how to care about usage. such that we can do linear type theory and also a whole bunch of other interesting things that have come up in the literature of usage annotations. I think this is kind of the most convincingly natural deduction treatment of linear logic that I've seen. And in particular, I don't think I've ever seen simultaneous substitution for linear type theory before, other than in my own work. Thomas Petracek is something kind of similar. But so the simultaneous substitutions are, if you remember the environment slide, where there has to be a matrix involved basically to things. Yeah, this is all agged up, so you can run the usage checker, which is quite nice. And what we've got to do, once I finish at Huawei, I'm going to hopefully write it up. We've got some idea of how to do recursion, which is where the difficulty is you have a continuation that gets used arbitrarily many times. So if you think about recursion over natural numbers, the successor case could come up again and again and again. You don't know. We've got a thing to make it work. Basically, you require all the usage annotations are kind of duplicable. But somehow it doesn't follow exactly from the linear algebra. So I'm kind of mildly suspicious of it. I mean, it seems to work quite nicely, but and yeah, well, we can ask about what type systems we can express. Can we do something like system F with 2 layers of interesting syntax? So interesting types, indexing, interesting values, interesting expressions. And there's this kind of general question that in Aleatal, the premise combinators and the Kripke stuff was basically they're all kind of intuitionistic connectives, whereas we required to do linear things, bunch connectives. And what's the connection? Why does that happen? I don't really have any idea, but it would be an interesting thing to know about. Okay, and that's all I have to say. Thanks for your attention.
Okay. Thank you, James. Can you hear me?
Yep.
Okay, thank you. Can you tell me, I mean, this is all very very impressive from a technical point of view. And but how do you evaluate this? How do you really say, oh, this is a good idea, what I've done?
I guess by dog fooding, basically. I mean, so hopefully, I suppose I'm the first person who should be using it. But hopefully other people might want to try it as well to see whether it's robust to things like can people working on, say, session types do all the things they want to do in this framework, or do they find something lacking? Basically, give it to the working meta theorist and see whether it really helps. So as I say, I think the usage checker is a kind of big win, because it's already helped me as the working meta theorist to, for example, write a example terms and have like a quick check that they're correct without re-implementing the same old shit every time. But yeah.
Did you find anything like what would you think is the most kind of relative to other techniques? Where do you think it's the biggest win here using your approach?
So I think it's at least a reassuring thing. I don't know how you go about evaluating this. I think it's reassuring that we're really doing this linear stuff in the same style as we were very happy doing for intuitionistic things and classical things. That we can really talk about variable binding and that being handled by this general machinery, and that we're using simultaneous substitution, which is, I mean, what after you do your first attempts at proving substitution for like simply type lambda calculus, eventually you talk to Bob or Connor or someone who says use simultaneous substitution. It all works out nicer. Now we didn't know we could do it before, but we now know we can do it for usage check stuff. So somehow that should be a win.
Are there any other questions?
Hi, yes, I have a question for James.
Yep. Hello.
Hi, James. Thanks for the talk. So the usage checker seems quite interesting. So I'm wondering, so if I understood that correctly, so it's saying that we could, so in principle, you could use the usage checker to start out with something like a simply typed derivation where you have context sharing type rules, and then you can possibly generate a number of like infer usage annotations and give out a linearly typed derivation or a number of them. Is that, did I understand that right?
Yeah. So yeah, nice to see you again, Nachi. So yeah, how this is implemented in the outer code, maybe you find this useful, is that you start off with a term that's, so this D, the description of the syntax is the same for both the unannotated and annotated term. The trick we play is that for the unannotated term, really the semi-ring of annotations is the zero semi-ring. So there's one element of the unit type, and it works as unannotated because there's only one possible annotation it could be. So we start off, we traverse this this thing where all the annotations are just TT, as you might like to call it. And I guess the key thing that makes this all tractable, because there's no magic going on here, it's but the key thing that makes it tractable is that we kind of already have the linear type information. Like we are still distinguishing between with products and tensor products, for example. Mm-hmm. It's just that the term we started out with might be ill usaged, not using things in the way the way we expect of the eventual usage check thing. So that's what's going on there.
I see. Okay. So because the reason I kind of bring that up is because in these kind of dependency analysis applications, like people worry a lot about whether a variable is used or not. Like, I don't know, security applications, or, you know, when you want state separation and so on. So it seems convenient to be able to look at a term and say, hey, it uses this variable or it doesn't, or to be able to say how many times it uses this. But I guess that might be like I was wondering if that was like a simpler case of what was going on here. Perhaps that is the case, because you also said that you just don't have the right annotations, but you still keep track of whether it's a product or a tensor product. So there's a lot more going on here, I suppose.
Yeah, the way I think about it, it is similar to a type checker in the AGDA sense of the word, at least, where you where you say what you want. You want this term to be of type whatever. So you kind of you say what you want up front, and then this checks whether you're fitting what you said. The sort of main difference is that while type checking should give a unique answer, for usage checking it's not so. You can have these weird things like if you prove top tensor top, then there are two with some variables in scope that the tops are going to use up. There are various good ways to use that. You know, there are various good good usage derivations.
All right.
Yeah, but yeah, I don't know. So in the application you were thinking of, do you think it would be reasonable to basically state I am using this variable or I am not using this variable and get it to be checked, or does it really need to be inferred?
So so inference is obviously convenient, because in the simpler systems that you don't start out declaring, right? Typically, you don't always have the support from the type system to do that. But perhaps just being able to check how many times a variables has been used is not so much of a difficult problem. I think you can just traverse the term and look at it. Perhaps the interesting thing comes in here, and even the non-determinism comes in here because of the linear operations, linear connectives. So did I get that right?
What do you mean by the linear connectives? Sorry.
Like the tensor product, for example, right? So if it were a simply typed derivation, checking the usage, the number of times the variable has been used, let's say we just had Cartesian products and exponentials or function types, that would be a straightforward syntax traversal. No?
Yeah, I see what you're getting at. Yeah. Do I know an intelligent response to this? Yeah, I think not exactly this usage checker would tell you, because it always makes the assumption that when at the point at which you bind a variable, you know how you're going to use it. I suppose you could iterate through the possible ways. You know, there are finitely many choices of whether you use a variable or not, and this will be able to tell you which of them are valid. So that's probably the best answer I can give. It's probably not a great answer, but
but thanks a bunch. We can continue this offline. Yeah, thanks.
Oh, yeah.
Okay, I am mindful of the time, so let's thank James again for his very interesting talk, and see you at our next public tech talk. Thank you. Goodbye.
Right.
Thank you, James. Fantastic talk.
Thank you.
Thank you.